All right, chapter 19, population ecology. So what we're doing here is we are broadening our horizons a little bit when it comes to organisms. We're now not just looking at their genetics, which would be a very, very tight kind of look, very close look at things, but now we're looking more broadly at how organisms interact with their environment. And so it's a little bit different from what we've seen before, but it's definitely going towards the bigger picture view that I was talking about. So the first part of this is to come up with some definitions. And so, as you probably remember, a population is a group of individuals of the same species at the same area at the same time. And the population is something we encountered before, because when we talked about evolution, microevolution for example, but even macroevolution, it was the population level at which evolution occurred. So this is already a very interesting level for us. But more than that, what we can do is we can look at how populations interact with their environment. And when we look at how an entire population of a species interacts with the environment, then that's what we call population ecology. If you recall from chapter 18, we had one level of ecology where we only looked at an individual. We call that organismal ecology. This here is the second level of ecology. So it's a little bit more complex than just following a single individual, but it's not that much more complex. And this is usually a good starting point to understand more about ecology. So what you need to do then is figure out something about how that population interacts with its environment, and in order to do that, you're going to come up with some characteristics. What would you want to determine about a population as it interacts with its environment? There are some very straightforward things that you can find out. Density, for example. How dense is the population? That's of course a function of how much area is available and how many individuals there are. Dispersion pattern. Dispersion pattern means if you look at this environment, where are they all? Are they all equally spaced, or are they just sort of any which way? Is there any rhyme or reason to how they are distributed in this environment? Another thing you can look at is age structure. How many of them are of reproductive age? How many of them are juveniles? How many of them are past reproductive age? So all those kind of things are important. And then lastly, another example would be growth. How fast does this population grow? Does it grow? Is it in decline? How many individuals are contributing to the population, and so on. Now, most of these types of data are not something that you can obtain by just sort of taking a cursory look at an environment. I mean, if you stand in front of the forest and you're trying to figure out, well, what's the population density of these trees, obviously you're going to have to count the trees. So you can't just get this information by doing a quick look. Population density is really a very difficult kind of parameter to estimate, and the reason why is because animals certainly don't stand still. Trees are things you can count because they do stand still, but they're also easy to miscount unless you actually mark them. Every single one you count, you mark it. And so obviously there are some challenges with this. Now in very basic terms, density is a parameter where you count the number of individuals and you divide that by the area that you find them in, or if they're in water, you can do it by volume. I mean, if you look at plankton, for example, those are very small organisms that you find in salt water. They are at the base of the food chain, and there's a certain amount of plankton per volume of water. And so that's another way of getting the population density. Now, if you are going to determine this, if you're bent on figuring out what the population density is, then one of the things you have to do is count how many individuals there are. Now, census. If I tell you census, you picture the census that we have in this country every 10 years, and you know that that's already a big deal, right? It takes a while. It's difficult to count everybody. People don't answer the door. They have all kinds of people that they hire and canvass neighborhoods to make sure that they're counting people, and likely they don't get it right anyway, right? So this is definitely an issue, counting an entire population. And here, in this particular case, you see a population of prairie dogs, and the problem with prairie dogs in particular is they, A, don't stand still, and B, they have burrows in which they can hide. So how are you actually going to count them? Well, somebody might say, well, we could somehow, you know, kill them all and then count the bodies, but that would be totally counterproductive because you're trying to figure out how the dynamic is between the population and its environment. So what you have to accept simply is that you cannot get an exact count. Understand that you cannot most likely get an exact count. Instead, what you're going to do is you're getting an estimate. And if you want to get an estimate of something like this, you can first of all define your area. So that's pretty straightforward. You can go to a field like this where you see a bunch of prairie dogs and say, okay, I'm going to take 1 acre of prairie dog habitat. I'm going to take 1 acre. And that is maybe just an arbitrary number. But at least you have something you can start with. And now I'm going to count how many burrows there are. Burrows in the sense of literally holes in the ground. And then what you can do nowadays is you can actually send probes and video cameras into the burrows to see what the burrow actually looks like. And when people study these burrows, they find that you have multiple entrances to a single burrow, and the average number of entrances for a burrow is something around 6. So that if you look at one of these burrows, right, then you'll find somewhere in the environment of that burrow there is a connection with 6 exits. So if you therefore count the number of holes in the ground and divide that by 6, that gives you an approximation for how many burrows there actually are, for example, right? The other thing you can do is you can position a camera inside some of these burrows and figure out how many of these prairie dogs are coming in and out. And you'll find out that, you know, a group of prairie dogs that runs through or uses a specific burrow numbers in the low teens. So it's maybe, you know, 12 prairie dogs that frequent one of those. So now you can calculate the number of burrows based on the holes in your area. And then based on how many burrows you have, you multiply that by 12, and that's approximately how many prairie dogs you have in 1 acre. And you see how tricky that can be, how many different things you have to do to get to that number, because you are always only going to get an estimate. So these are not very straightforward kinds of things. Sometimes you really have to deal with some tricks. But in any case, once you understand how the organism works, it is actually really straightforward to come up with estimates. Now, it is an interesting fact that our census, the way we census the people in the United States, costs a little bit over $1 billion to do. That's how much it costs, okay? Now, using publicly available data on insurance, on tax returns, on driver licenses, on various kinds of things that are publicly accessible, scientists have created estimates. For the last 3 censuses, they have tried to create estimates based on those kinds of data, as opposed to sending people knocking on doors. Do you follow that? Do you see the difference, right? Now, when the scientists do this, using the internet and using publicly available data, the cost is about $1 million, because it takes some hours to do this. 1 million versus 1 billion. And the difference in the number that they come up with is about 1%. So you can accept that you're going to do an estimate, and you are going to be able to get to the same number, plus or minus 1%, for 1 million as opposed to 1 billion. And yet we do the census because we have a bureaucratic apparatus that is ultimately self-permeating, right? The people who are in charge of the census, they're not going to say, oh, let's not do a census. They have a mandate to do a census. But it's just something to think about. As time passes and as we're better able to make estimates using cheaper means, maybe we should. It's just something to think about. So population density is one of the key things that we need to learn about a population. Patterns of dispersion are another kind of data set that we can look at. And you'll find that these types of patterns come in three forms. The first one of these is a clumped dispersion. And clumping means that there are certain numbers of organisms, maybe just a few, maybe a bunch more, that cluster together. And they cluster for a variety of reasons. If you look at a school of fish, they cluster because there's strength in numbers. If you look at perhaps a set of plants that cluster together, it's probably because the mineral content in that area of the ground is very useful or very appropriate for that kind of plant. So there are various reasons why there is clumping, but there are lots of things in the environment that force clumping. To give you an example, let's think of a cow patty. Everybody know what that is, right? Now, a cow patty, turns out, is a very nutritious environment for certain types of insects. And therefore, if you're looking for those particular kinds of insects, certain types of flies, as well as certain types of beetles, then the easiest way to find them is to go and find a cow patty at a certain stage, a certain age, I should say. And so fresh cow patties will attract certain types of flies. Older cow patties will attract certain types of beetles. And then when the cow patty is dried out, then it will attract certain types of humans because they can take it home and burn it. Right? So there's all kinds of reasons why cow patties are useful, and they are a reason why clumping occurs. There's also a type of dispersion pattern called uniform. And uniform means that the individuals of the population are essentially spaced out equally. And here you can see as an example the penguins. These are breeding penguins. And each of these individuals has an egg that it's incubating. So the egg is basically under here. Those of you who have watched things like Happy Feet or something like that, you have an idea of what's going on here, right? And so these penguins literally will poke and peck at each other when somebody tries to walk through, because this is the way they have their little own space. They have an issue with personal space. And so we tend to have a uniform dispersion pattern when organisms, by their behavior, want to have a certain amount of space around them. And then lastly, in some instances, there are no real reasons for why there is any patterning. There is no behavior, there is no resource reason, and as a consequence of this, you may end up with a random dispersion pattern. If the environment is very uniform and basically anywhere you go the conditions are great, then it doesn't really matter to you where you end up. And trees in a rainforest tend to have that kind of dispersion pattern. So you're looking at a rainforest in this case, and of course you can't even see individual trees, but if you were to look for a certain species of tree, you'd find that it's sort of haphazardly distributed throughout this area, and you would realize it's pretty random. It's just by chance of where these seeds fell and where these trees grew. So random means that there is no real reason for being dispersed any particular way. It turns out that when you look at populations, many populations display more than one dispersion pattern under different conditions. And so for humans, you find that the conditions can be different, but you can also find that it depends on the scale you're looking at. I mean, think of parking stalls. There, the dispersion pattern is by nature of parking spaces is uniform, right? I mean, you're spaced in a certain way. So when you're in the parking lot, you find that this is a uniform type of dispersion pattern. If you find somebody who parks sideways across 3 spaces, you get upset, right? And so as a consequence, this is, pretty much earmarked. However, if you use something like, Google Maps or something, and you zoom out a little bit, you'll find that there is a parking place, and over there, a few blocks away, is another parking place, and over there is another parking place. So the parking places themselves are clumped if you look at the higher scale. And so as a consequence, it really depends on scaling in this case. Here, for example, you can see that the people who are sitting on the beach, they tend to have a very uniform distribution. And that's based on us wanting our personal space. Now imagine for a moment that you arrive bright and early at the beach. You know, you go to Venice and you think, okay, this is great. I got this beautiful day and the beach is still empty. And you put down your umbrella and your towels or whatever, right? And you're planning on having a nice time. And then another family comes, and with the entire beach to choose from, they're going right next to you. What do you think? You go, come on, people. Oh my God. Right? With the whole beach to choose from, you're gonna come right. That would be odd. And so, therefore, you would expect there to be a uniform dispersion pattern. You want them to kind of keep their distance. Then if you go to the level way up, you can look at the coastline, not just the beach, but you look at the broader coastline. There is a city here, that's Boston, Massachusetts, Providence, Rhode Island, and of course New York City. And so clearly you can see that there are population centers. This is Hartford, Connecticut. There's New Haven, Connecticut. So there are various population centers, and the question is, why is this dispersion pattern clumped? There must be a resource, because clumping has to do with a resource. The resource in Boston, Providence, and New York is a safe harbor. If you want to bring your boat in for trading and you want it to be safe from the elements, then that's what you need. And then, of course, if you go along a river, then you sometimes find areas where the river meets the ocean. That would be New Haven. And then you go inland on the river, and where the river stops to be navigable, that's where you find another population center, because that's where the boats have to stop, and that's where you have to bring all the stuff, right? And so that's why you have inland centers as well as other centers. So those are the kind of things you can see on a larger scale. And then you go to places, you know, in our area, you go west of the freeway here, and you go to sort of New Victorville, right? And you'd see all these houses, and they're definitely uniform. Everybody has a sixth of an acre. Everybody can stretch their hand out of their bathroom and touch the other house. That's how they plan these, I think, sometimes. Anyway, it is what it is. This is how people live, and it's just a division of resources. So these are the kind of patterns you will see.